Let's take a look at ionic bonding. So as we stated, this is that electrostatic attraction. So it's just the attraction between, I can't talking right. The attraction between a positive charge and a negative charge on atoms, which means between a cation, which has a positive charge, and an anion, which has a negative charge. So we typically just represent ionic compounds by their chemical formula. We don't typically draw them out into large structures because they take on a pattern of like placing the atoms relative to one another in an ordered pattern that is typically a solid, or they're going to be ions floating or distributed within water surrounded by water molecules typically. So it's either they're dissolved in water or they tend to form solids. And that should hopefully intuitively track with like how you use table salt. But we can look a little bit more at their bonding that we represent in that chemical formula. So if you wanted to know what type of ionic compound or what types of ionic bonds would form between two elements, we would follow these 3 steps. We would first use the octet rule to determine what ions would form from those elements. So I'm using the example of sodium chloride. So our metal is the sodium and our nonmetal is the chlorine. And right here, I have their electron dot symbols. And for the element. Now, we're going to try to use the octet rule to determine what are the ions that would actually form. So our sodium has 1 outer electron, and our chlorine has 7 outer electrons. Our metals will tend to form cations, and so they'll lose electrons. They have less of those outer electrons anyway. And our chlorine, being a nonmetal, is more likely to be negative, so it's going to gain electrons to satisfy its octet rule. So our sodium will lose 1 electron, and our chlorine will gain 1 electron. And we'll have then sodium plus, and that plus represents an imbalance between protons and electrons, where there's more protons, is another way of saying it's lost 1 electron. And our chlorine now has 8 electrons in its outer sphere. Outer electrons, our sodium now is 0. And it takes on that -1 charge that says I have 1 more electron than I do have of my protons. And 0 outer electrons or 8 outer electrons are basically the same thing. If you have 0, then it kind of, you've got an empty kind of outer layer. And so you go down to the next layer that was filled. So it'll have 8 outer electrons too. Kind of a glass is half full, half empty way of thinking about it. I still like using the 0 and the 8 because it helps reinforce that the sodium is the positive and the chlorine is the negative. So now what we want to do is combine our anion and cation in a ratio that would balance the charges. So overall, it has no charge associated with the compound of both sodium and chlorine ionically bonded together. So in this case, we have +1 and -1. Those perfectly balance each other out. If I add them up, they're going to equal 0. And so we have, we can think of it as a 1-to-1 ratio of sodium to chlorine, but we would represent it then with NaCl. And we don't use any subscripts here because the subscript would be 1. And we omit anything that's 1 because if we're writing the element symbol in a chemical formula, like, well, there's at least 1 atom, right? So we only put a subscript if it's more than 1 because, I don't know, we like to abbreviate even more than we need to. So if, just by way of example, we had an imbalance where we had, let's say, sodium plus and oxygen, which would form a -2 charge. Our oxygen has 6 outer electrons, so it's going to need 2 more to get to 8. Then if I was balancing these out, it wouldn't be a 1-to-1 ratio anymore because then I would have more negative charge than positive charge if I brought just one sodium and one oxygen. To balance out this -2 here, I really need a +2 for my sodium. Therefore, I'm going to use 2 times the +1 charge to create that. That means I'm going to need 2 sodium atoms. And this will look like Na2. Oh. And that'll balance out to be an overall charge of 0. I'll have 2 +1 charges and a total charge of 2 -2 charge from the oxygen, which would, if I added them up, equal 0. And this is about as far as we will take ionic bonding. It's important though to I like these pictures of the solids. They help me out quite a bit. So here's sodium chloride again. And when we write sodium chloride, we're really expressing the ratio of the atoms relative to one another in its most simplistic form. But there's lots of these atoms in one crystal of salt, and they're alternating. So the negative charges are as surrounded by positive charge as is possible. We want to maximize the amount of opposite charges touching and minimize same charges repelling one another and touching. And so the pattern that's created, we call it a crystal structure, but is highly uniform. And we'll see this alternating cation, anion, anion kind of pattern. In general, these compounds will dissolve in water. Not all. It depends on how big the charges of the ions. And that means that each of these ions will separate and be surrounded by water molecules. And we'll talk about that a lot when we talk about solubility later. We call these salts a lot in general, and whenever we have a metal and nonmetals bonded together ionically. And the interesting thing about these two is they actually melt from the solid state to the liquid state at very high temperatures. So while they easily dissolve in water, and then they have this like liquid property because the water is getting in between all of the different ions. It's really the water that's the liquid. If you take just the sodium chloride without any water around and you just heat it, it'll heat up into the thousands of degrees Celsius before it actually melts. You get these molten salts. They're actually pretty cool. Yeah, and so they will conduct electricity when they're dissolved in water because they have all these charged particles floating around. They're great. And like sodium chloride, it's super tasty.